This is Brett Sanders, and this is the third introductory video for using PRIMo. In this video, we are going to configure PRIMo for point sources. Point sources represent points within the model domain where a flow of water can be added, such as for a river inflow or for the outlet of a storm drain. Now, my screen here is set up with a number of different windows. We can start off with a reminder that PRIMo can be accessed as a zip file, and when you unpack the zip file, you'll get a number of different MATLAB scripts, you'll get a project directory, you'll get the source code, and the source code can be compiled to generate a binary, which sits in here. I've already done that, so I won't repeat those steps now, but if you want to see how to do that, you can go back to the very first video. Okay, now to refresh your memory, in the first setup of PRIMo, what's available as input files when the code is downloaded and first used is a scenario where a model domain in Miami is configured and the flooding is simulated for the case of simple, straight, uniform rainfall rate. This graphic here shows the spatial domain for this Miami-Gate test problem, and the first test case, if we run that with this script called PRIMo-Viz, we can see the results of that test case. The rain comes down, the water accumulates on the land surface, and it begins to puddle in low spots. The second animation shows results on a coarse grid showing both the water surface elevation, and additionally there's a color coding here to indicate how deep the water is on that coarse grid. Okay, what we'd like to do in this video is illustrate how to add point sources that represent inflows of water. So what I'm going to do is I'm going to add 2 point sources to this model, one up here in the upper right hand corner, which is sort of a more inland location along the Miami River, another one on this drainage channel here, and it's going to be a simple test case that just shows basically simulating water flowing down these canals towards the outlet, which is located here. Okay. So to configure these point sources, it's helpful to go back to the original PRIMo prep script and rerun that and just have a plot like this one, which shows the spatial coordinates of different points on the screen. So if I'm interested in adding a source, say up here or down here, I need to give the input file both the X location, which here is a longitude, and a Y location, which is here a latitude. And I'm going to do that inside of a text file, which is labeled miamigate.pointsource. Of course, if you had a different test case, like say New York City, it would be newyorkcity.pointsource. So we'll open this up with a text editor, and what you'll see is a tabular file format where the first input is a label that's just a reminder of how many sources are being added, and then the actual number, which is an integer, and then the next row of this file is a line of text which shows you the headers for each of the columns of the data that need to be input into PRIMo. So this is set up for 2 different point sources. The file format for this tabular point source file is to have an ID, which goes 1, 2, 3, 4, 5. Then there's an option called use file. So if option is set to 0, it will not use a file, and the model will specify a constant point source given by this number, which is the sort of 1, 2, 3, 4, 5th column in the file. If you set this to 1, which is yes, then the model will open a text file which has a time series of inflows stored in it. For now, we're going to do constant inflows. The inflows will be entered at a flow rate of 10, in this case, cubic meters per second, which is a completely arbitrary number meant to just serve as an illustration. And then these 2 numbers here represent both the X location, or the longitude, and the Y location, or the latitude, of the point sources. So how do we come up with this number? At an earlier time, I zoomed into these areas and came up with numbers that made sense. So you'll notice that this one with the latitude of 25.8088 takes me up here, and also the X location brings me down here. So that gives me this location. And the second point is 25.709, which is down in this region here. And the X location is minus 80.264. So 264 takes me somewhere out here. So this other point source is going to be located here. So you can see it's a pretty tabular, simple setup there. Now we go back, we save this after we made the edits. Clearly you can just go, it's a text file, you can just change these numbers around and edit them the way you like to get the points in the right location. Then we go back to the main input file, and right now the file is set up as it was initially configured, which is to configure a rainfall event with a rainfall rate of 100 millimeters per 60 minutes, or say 10 centimeters per hour. For this illustration, I'm just going to turn the rainfall off by setting the rainfall rate to 0 and using a constant rainfall rate. And then I'm going to turn on the point source option. So then we save this file. Once this is turned on, we get the model opening a, should read load star.input file. Not input, but point source. Point source. So make that change. So if one, you should be loading a point source. So once that's configured, we can go back into the command window. We've already compiled PRIMo. If you haven't compiled it, you can put in a gfortran-o bin /PRIMo-GPU source /PRIMo-GPU.f90. The Fortran compiler will generate the executable. This warning comes up each time in my computer. It's not a problem that prevents the model from running. So now I'm going to go ahead and execute the code by saying /bin PRIMo-GPU, and then the name of the project I want to run, which is Miami-Gate. So the code has is running here. There's some output written to the screen. It says it was able to read the input files. It was able to create its upscale grid. It set the initial conditions, and now it's running. And then if you wanted to see how the model's coming along, you can load this file here. You can see it's already finished. The model ran. It took 19.7 seconds to run. There's a report on the mass conservation, which is 10 to the -9, which is excellent. The mass conservation report says it starts off with no water in the system. At the end of the system, there was 72,000 cubic meters of water. All that water came in from point sources, and all the other terms are set to 0. So it's a pretty simple mass balance where you have a dry, empty domain to begin with. Water enters through a set of port sources, and then at the end of the model simulation, the water source is shown here to be that same amount. This number is interesting. We ran the model for an hour with 2 sources at a rate of 10 cubic meters per second. So the total inflow rate was 20 cubic meters per second. We ran it for basically 36 hours, and voila, we get 72,000 cubic meters per second. And the reason it's not exactly 72,000 cubic meters is because the model ran a slight fraction past 3,600. That's why it's not exact. Okay, so the model ran. Now we can go back to the visualization script called PRIMo-Viz. This is already set up to open the Miami-Gate directory. It's set up for a model that has 10 outputs saved with a time step interval of 360 seconds. It's set up to load both to output both a fine resolution depth animation and also a coarse resolution animation of the free surface elevation and the water depth. So we can run that. Now you can see the effect of these sources is to create a flow which sort of runs down the channel. This, and then also runs down this channel. You might ask, well, why did this channel flow stop right here? And the reason why is because there was a high point in the ground elevation in the DEM which created a blockage feature. And the water would have to accumulate more in this channel, either for a longer period of time or from a higher flow rate, to get over that feature and move its way down the channel. So why don't we go ahead and sort of do a second run where we crank up the flow rate or the duration, or maybe both, to see like how that changes the results. So we can do that easily by going back to the input file, rather the point source file. We can double the flow rate coming into both of those sources. We can also run this model for, say, instead of 1 hour, how about 72 hours? And maybe we'll save the same number of time steps by saving results every 720 seconds. So let's run that model one more time. Yeah, if we were to, say, zoom around here, we might be able to see more clearly that there's a bit of a topographic obstruction right in here. And that's the reason why the flow is getting blocked by that high point in the channel bathymetry. Bathymetry is often a weakness in models. Bathymetry data are often hard to come by. Bathymetry changes quickly with storm events, sedimentation, and so on. So ongoing challenge for calibration and validation is getting good bathymetry data. So now the model finished. Maybe out of good habits, we can check the log file. Once again, model ran, in this case, 7,200 seconds, took 48 seconds. Mass balance was good, 10 to the minus 7th. Everything else checks out. So now we can visualize this scenario. Higher flow rate, longer simulation. Water runs all the way downstream, fills in the ponds. And this sort of makes intuitive sense. So now you might ask, okay, those are constant point sources. How could I model a scenario with time-dependent point sources? Going back to the input file, we have this option to switch from a constant to a time-dependent source, as described in an input file. The input file format is provided with some sample files. So if you go into the time series directory, I've got 2 sample input files here. So I'll open one of those up. And in this case, there's a number of different lines of header information, a streamflow record, a station number, start time for the data, and then it tells you that line 8, which is here, is the length of the record. Line 9 is the time interval of the data in minutes, and line 10 is a time series of actual values. So this is 15-minute data, so we've got really several hours of flow rates here that can be specified. So, and there's a second file that's pretty similar to the first one. These are just hypothetical files that are sort of just samples to exact same information actually, but to provide an example of how you could create a record for 2 different gauges, 2 different locations where you want to add flows, have a time series of the flow rate, and add it to the model. So why don't we go ahead now and save our input files. So we're going to make sure that this guy is saved. I'll hit save there. We're still just using the point source option. We're going to make sure this one is now saved, and we'll go back to our terminal window where we run the script. Not run the script, but run PRIMo. And you can see, I guess, while we're waiting, how handy it is to be able to run PRIMo on a desktop where you have MATLAB running, and you've got a Finder, and you've got a text editor, and you've got a terminal window. It's a pretty nice way to do interactive modeling, and it becomes more challenging on bigger spatial domains, and that's why we have the PRIMo-GPU functionality. So you can send the job to a GPU, run the model quickly, and then bring it back to your system, or do the MATLAB work on a remote server. That's another possibility, to have a more interactive modeling environment. So the models now run with this time-dependent forcing. We can, I guess, again check the log file. We can see that it ran the 7,200 seconds that we wanted. It took about 27.7 seconds to run. The mass balance is excellent, and a little bit more water came in than before. When we used the 10 cubic meters per second rates. So let's let this run. Create a visualization. Water creeps down, gets over the bump. Not quite as wet as the previous scenario, but maybe a little bit wetter than the first scenario that we were looking at together. So this is the wrap up for video number 3, using point sources to specify inflows of water into PRIMo.